Well, good evening, everybody. I want to welcome you all to the 2012-13 Fuzzy Vance Lecture in Mathematics. So for those of you who are too young to know, Fuzz Vance, who was not born with the name Fuzz Vance, but was actually Elbridge P. Vance, was a longtime faculty member and a 29-year-long chair of the Department of Mathematics. And these lectures we have once a year are in his honor and in his memory. And I would like to first, before thanking our speaker for coming, I want to thank the alumni donors who made these lectures and the visit by Professor Goldman and his predecessor, distinguished visitors, possible. Particularly, I'd like to mention Dan Orr, alumnus of Oberlin College, who passed away last summer and has been a big supporter of various activities and initiatives in the mathematics department. And for those of you who haven't already noticed, there are refreshments, and I hope there'll still be a few left after the conclusion of this lecture tonight. So I would like to introduce William Goldman, Professor of Mathematics at the University of Maryland. Professor Goldman has a Bachelor of Science degree from Princeton and a PhD from the University of California at Berkeley, and he has studied under some of the very greatest contemporary geometers and topologists, including Bill Thurston, Fields Medalist. He's held appointments, in no particular order, at the University of Colorado at the Mathematical Sciences Research Institute in Berkeley, also known as MISERY, and at MIT. And it's actually at MIT where I first became acquainted with Bill Goldman a long time ago. He's also held visiting positions at Oxford and Paris and Barcelona and Djursholm, Sweden, at the Mittag-Leffler Institute most recently. He's done it all. He has published dozens and dozens and dozens and dozens and maybe dozens of research articles on geometry, topology, particularly the geometric structure of manifolds. He's also written a book on complex hyperbolic geometry. He's supervised 26 doctoral students. Along with Rick Schwartz, he founded the Experimental Geometry Lab at the University of Maryland. This was featured in Scientific American. He now serves as the director of that lab. In 2007, he received the Distinguished Scholar Teacher Award from the University of Maryland. He gave an invited address at the most recent International Congress of Mathematicians in India. That was in 2010. And he served on numerous committees of the American Mathematical Society, and he was elected to the Council of the American Mathematical Society in 2006. And he is one of the inaugural class of AMS Fellows elected, or named, I should say, last year. And beyond that, he plays jazz piano with abandon. And tonight we're going to learn how to play pool on curved surfaces, and he's going to disassemble and teach us the wrong way to add fractions. Thank you very much.
Well, thank you very much. It's a pleasure to be here. What I'd like to discuss in this lecture is the nature of mathematics, or its various natures, and in particular how it's simultaneously a science, a language, and an art. And I'd like to discuss how this unique collection of three natures of mathematics leads to challenges in its study, its dissemination, and its teaching, and why we should invest in mathematics, because it's investing in people. I'd like to concentrate the technical part of the talk on two interrelated problems in math. One occurs from science of trying to understand how a billiard ball moves on a surface when it's hit by the cue stick, and how that leads to a very interesting dynamical system. And then I'd like to discuss how mathematics arose in art and also in nature, and discuss properties of the golden ratio and number theory. And in particular, these two problems of playing pool on curved surfaces and properties of the golden ratio are very closely related. So let me begin by discussing the scientific aspects of mathematics. So natural phenomena are understood through quantitative measurements, and the quantitative measurements are numbers, and they're abstracted into mathematics. The numbers are then manipulated rigorously by rules that we think can't be broken to make predictions. And these predictions are in the form of abstract and very general mathematical statements which describe a language. And in this way, mathematics is the language of science. However, it's an idealization, and mathematics represents a situation which doesn't really occur in real life, but it's an approximation. And as we understand more and more and make more measurements and manipulate them and digest them and refine them, then mathematics grows, and the situations that we want to model are approximated better and better by these idealizations. So for example, in classical physics, rates of change are governed by the laws of calculus. For example, the force is mass times acceleration. So acceleration is a second derivative of the position, and the force is the external force that a particle might be under. So let me begin with a problem of understanding billiards. And we imagine a square or rectangular pool table, and we hit a billiard ball following a straight line at constant speed. And I'll give a computer animation to show this. And the first example will be a billiard ball on the square. And on the square, we'll imagine sending the billiard ball off at an angle which is 45 degrees from the side. And it'll bounce around off the sides of the table and eventually come back in the same direction. It'll be periodic. Then I will do the same experiment on a rectangular billiard table. And on the rectangular billiard table, the path will still be periodic, but it'll be a different period. And the shape of the table and the slope of the trajectory of the billiard ball can be detected by the sequence of numbers detecting how the ball intersects the various sides. So let me switch to the billiard table. So here we have a ball that's moving around on the table. The table is a square, and the ball is pointed 45 degrees up. And you can think for a bit about how the path that it follows, but it's after it hits the bottom, it hits the left, and then the top, and then the bottom again. And by reading off whether it's hitting the horizontal sides or the vertical sides, we can detect what the slope of the ball is. And we can use this to understand the properties of the slope as well as the properties of the system. So the second example I want to give will be on a rectangular table. And notice here that the ball bounces back and forth between the top and bottom 3 times before it hits either the left or the right. And in this way, this is a rectangle where the top is 3 times larger than the vertical sides. And again, we're aimed at 45 degrees. And we can detect the size of the billiard table from the sequence of sides that the ball intersects. And finally, let me go back to the square billiard and think of another way of relating it. Here's a different perspective on the original square billiard. And so this is where we come up with a surface, and we can understand the property of bouncing in maybe an easier way by unfolding this square into 4 squares. So you imagine that when you cross the left side here, you're crossing, say, the left side here, but coming back on the other side. So here, we just saw the ball cross through here, but come back on the other side. We can replace the square with the reflections on the sides by a surface that's obtained by taking the larger square and identifying the top to the bottom and the left to the right. In this case, we're just going straight, but each time we leave the bigger square, we come back on the opposite side. And this is a way of understanding a generalization of this simple problem of hitting a billiard ball on a billiard table by a motion of a curve on a curved surface. In this case, the surface is a torus. So in both cases, I was looking at paths where the slope was 1, but you can easily imagine that if the slope is any rational number, the properties of the numerator and the denominator will represent the number of ways and the number of times we hit the vertical side before going to the horizontal sides and vice versa. When the slope is irrational, it's much different, and the path never closes up, and eventually will fill up the whole rectangle. So here's an example of the interrelationship between 2 seemingly different areas of mathematics: number theory, the properties of numerators and denominators of the slope of the trajectory or the size of the rectangle, and differential equations as modeled in this dynamical system. Let me now describe how we think of this in terms of the mathematics. So we want to abstract this notion of a billiard table. And the same differential equations that govern the motion of billiards on a rectangle can govern all kinds of other phenomena, such as population growth, finance, chemical reactions, because the patterns are similar. And the patterns don't really depend on how large or small the system is, but are independent of the size, and what's true in the small is true in the large. Furthermore, the added abstraction of mathematics means that it's reproducible, that we don't need to be actually working on a billiard table to do these experiments, and we don't need to be able to measure motions of comets or very small objects that we're trying to mathematically model. The mathematics is the progression of ideas is governed only by abstract logic, and we don't need special equipment or exotic environments to do our experiments. Just working conditions in which we can think clearly. Let me now go on and describe some of the linguistic aspects of mathematics. The whole point now is to take patterns that we see, abstract patterns, and we promote them into primitive mathematical concepts. We want to break complicated relationships between them into simpler ones. and consolidate the definitions and take the ideas and put them together to make new concepts. And so, throughout this talk, I'll be describing how mathematical ideas in the body of mathematics grows. And that leads to certain challenges in trying to understand and communicate mathematics. In particular, it's very important to know what the right question is, to know which are the right patterns to notice. And sometimes finding the right question is just as important as finding the right answer. But we give ourselves the liberty of changing the questions to fit the answers. So we might take an original question that we're asked to solve, and, well, we make some assumptions that may never actually hold, but at least we can get a good answer for it. And then having done that, we can go back and see what assumptions we made that can be weakened, and then try to answer that new question, maybe get a better answer, and eventually we get a sequence of approximations to the original question. But in the process, the subject grows and grows, and the body of knowledge grows. Asking and answering questions about the simpler concepts creates new mathematics and new concepts. Keeps on going and growing. In particular, I think it's true that more mathematics has been created in the last 50 years than in all of the preceding human history, and that creates a major challenge in getting up to the levels of current research. Is how do you learn enough of what's already been done to be able to do something new? Let me now turn to the artistic aspects of mathematics. And so the example that I want to give is illustrated here by the Parthenon. And the architects building the Parthenon were fascinated by a certain number that I'll be discussing, the Goldman ratio, which is 1 plus the square root of 5 divided by 2. And you'll see several ways of thinking about that number. And they thought this was the most beautiful form of a rectangle. And this number appears not only in art and architecture, but also in biology and nature. And I'll give an example of that. And so the ancient Greeks were aware of the ubiquity of this number, and so they thought of this as a model for beauty. In particular, this is a familiar pattern in many unexpected and surprising settings. And when you see something familiar, it's reassuring, but it's always empowering and fascinating. And the patterns in which old patterns are broken lead to new patterns. So the Goldman ratio is this number here, 1 plus the square root of 5 divided by 2, and that's the last time I will write that. Its decimal approximation is this number, so it's about 1.6. And it appears in many natural situations, which I won't describe, but here's one. This is a seashell, and the proportion between the various distances here as the shell spirals out is the Goldman ratio. So I'll refer to the Goldman ratio as phi. So it's 1 plus the square root of 5 divided by 2. Knowing what the Goldman ratio is, the 1 plus the square root of 5 over 2, that's a solution of a quadratic equation which can be written in this form. And this leads to a very nice sort of fundamental reason for studying this number. This leads to a recursion which lets us approximate the number phi in a really fascinating and beautiful way. So we start with this equation. We write phi as 1 plus 1 divided by phi. And now we take this occurrence of phi and replace it by the old one. And then we do that again and again. And eventually we get an expression for phi by an infinite object in which phi only appears once, namely this infinite continued fraction. Now, so by going from its definition, which is this quadratic equation, to this gives us some interpretation of this number. However, we don't know what it means. So how do we give it meaning? So this is an example of changing the question to fit the answer. We have this number that seems to have this infinite form, and we can cut off this infinite form at a finite stage to get approximations. So we start with 1. It's a good place to start. And then we take 1 plus 1 divided by 1. That's 2. Then we take 2 and feed that into the recursion. So 1 plus 1 divided by 2 to get 3 halves. Now we feed 3 halves into the recursion. So we have 1 plus 1 divided by 3 halves to get 5 thirds. Do the same thing to 5 thirds, we get 8 fifths. Then we get 13 eighths. The numerators and the denominators in this sequence of fractions are the Fibonacci numbers, which themselves appear in many natural situations. And they're defined as follows. And this is, we start with 1 and 1. That's 2. Now we add the 2 preceding numbers. 1 and 2 give 3. 2 and 3 now give 5. 3 plus 5 give 8. 5 plus 8 is 13. That's the numerator here. And you can see the pattern of numerators and denominators in this sequence. 8 plus 13 is 21. 13 plus 21 is 34, and so forth. This is the same sequence that you would see if you took a billiard table that was in the shape of the Parthenon, where the sides were in the proportion of the golden ratio. And so this is the connection between billiards and this sequence of fractions. There's a very interesting pattern that one sees, and this is the wrong way to add fractions. So look at the sequence of numbers that we get approximating the golden ratio. Each fraction is obtained from the preceding pair by adding the numerators and the denominators. So this is not the way we're supposed to add rational numbers. It's a much more complicated way, but if you were to give somebody these 2 fractions and ask them to add them, this might be the first attempt, and the first attempt is usually wrong. But in this case, it's very useful. So this is called Ferry addition, after Ferry, and I'll say a little bit more about him in a moment. So here's the sequence of approximations for the golden ratio. 1, 2, 3 halves. 3 fifths plus 2 thirds added the wrong way gives 8 fifths. 5 thirds plus 8 fifths added the wrong way is 13 eighths, and so forth. 21 thirteenths, 34 21st, so forth. And these are the approximations to the golden ratio. Here's another way of looking at the same phenomenon. Let's fix some large number, n, and look at all the fractions whose denominator is no bigger than n. And then any fraction is obtained by the 2 closest one by this Ferry addition. So for example, if you take n equals 1, these are the fractions these are the whole numbers, and 1 over 1 is obtained by Ferry addition of its 2 neighbors, 0 and 2. N equals 2, here are the fractions whose denominators are less than or equal to 2, and you can check that each one is obtained from its 2 neighbors by Ferry addition, so forth and so on. So just take a random one here. You have 1 and 4 thirds gives 5 fourths as the product. Here, most of the time you'll get you have to reduce the fraction. 5 plus 3 is 8, divided by 4 plus 2 is 6, and dividing by 2, the numerators and denominators give you 4 thirds. So here's the sequence that you get when n equals 6. So the person who discovered this pattern was John Ferry, who was a geologist, and he was led to thinking about this through studying sound. But this is quite different. This is a quite different application than sound, illustrating the universality of mathematics. So these results go back to 1816. So let me move to a more philosophical discussion about how mathematics is created. So we first find a pattern, and we want to isolate the pattern. meaning that we want to focus on the essential qualities. And that's going to be how we form a definition. And then we promote it to a new concept by describing a definition. And this will be in our very rigorous language that's connected through logic. And then we relate it to the old concepts that are already defined by theorems. And these are theorems that are rigorously proved by abstract logic. So it's very important that this first step is done correctly, because if we have the right definition, that'll make the theorems much easier to prove. And we want to have things that are very simple and concise so we can understand them. So it's very similar to art in that we're taking an abstract pattern and representing it. This leads to various challenges in creating mathematics and training people to do mathematics, communicating mathematics, and explaining it. So there are a lot of things going on here. So in my opinion, mathematics is a very successful human endeavor. It goes back thousands of years, and it's continuing to grow at an exponential rate. But I don't think we really like to throw things away. So that means that a lot of mathematics accumulates. But it doesn't get just started, but it gets condensed because we find the right notions and then abstract them into definitions to get more powerful definitions, which include a lot of the old ones, but it condenses the former ideas. And this leads to many challenges in disseminating, organizing, and teaching the subject. So as more relations are understood and the subject grows, the ideas generalize, the subject becomes more and more abstract and more specialized. Well, the specialization and the growth lead to many problems in organizing it and trying to keep track of mathematics. So despite the basic unity, which we saw in the previous examples of mechanics being related to number theory, there's a natural tendency to splinter. And I've heard many examples of math departments where there are two colleagues that have offices next to each other that find out after several years that they're working on the same problem, but they haven't really ever talked to each other because they didn't realize it was the same problem. And they were in different fields and speaking, in some sense, different languages. And the specialization must be controlled and resist as the subject develops and grows. And I think it's, in the last 30 years especially, it seems like it's been very hard to just work in one narrow specialty without trying to understand others and seeing how things are interrelated. And that makes it even harder to learn because although there are books and books that are written about mathematics, the points of view change very rapidly. And the influences from other areas of mathematics are more prevalent. So as mathematicians, we're the speakers of a specialized language, but we're not just the speakers, we're also the audience, and also the practitioners, and the developers, and the first users. So there are various roles that we are playing, and they're all interrelated. And I think it's very important in the subject of mathematics to communicate. It's important to build a community of people that are technically literate and creative in our approach to the subject. So this is a picture when, in 1995, I took on the job as the director of graduate studies at the University of Maryland. And my oldest son is an artist, and I commissioned him for this cartoon to depict how mathematics is done at the University of Maryland with Maryland terrapins studying the geodesic equations for that are the straight lines on a curved surface. So this is what I told the entering class of first-year graduate students in 1995, that their graduate careers would be like. A few years later, I was involved in setting up the experimental geometry lab at the University of Maryland. And here's an example of a demonstration of the, one of the activities in the lab. Some students from Potomac High School were visiting the University of Maryland, and we set up a little demonstration of some of the mathematics and the mathematical software that we were using in the lab. And I think through the lab, we were really trying to get people interested at a very early stage. And this is a model of what the National Science Foundation calls vertical integration, of having professors talking to postdocs, and postdocs talking to graduate students, and graduate students talking to undergraduates, and undergraduates talking to high school students that are interested in mathematics. And so there's a lot of work for everybody at these different levels. So why should people invest in mathematics? Why is it important? And it's maybe easier to convince people that we should invest in a science rather than an art for getting funding, but all three aspects are very important. And I think, our society needs people who can learn and work with abstract ideas and communicate them effectively, all in a short period of time. And I think most of the people that we train at the undergraduate level and graduate level and postdoctoral level, even if they're doing high-level research, they may not be spending the rest of their lives doing research or doing research in the area that they wrote their thesis. But many employers are still impressed that people can learn something as complicated as theoretical mathematics in a short period of time and then be able to communicate it and teach it. And this is a valuable skill. So here's a drawing of some of the activities in our experimental geometry lab. And this is a quiz question for people in Jack's class. Which model of the hyperbolic plane is this? Right. So this is the conformal model. These are all triangles in hyperbolic geometry that have infinite perimeter but finite area. And this is a regular tiling, so all of these triangles are the same in non-Euclidean geometry. So in summary, mathematics is at once a science, a language, and an art. It's a rigorous, exact discipline, formulating statements, modeling natural phenomena that occur in many different areas. It's a language, it's a collection of ideas that are represented symbolically and organized into units of communication. Statements that are definitions and theorems, and they're all interrelated by logic. And it's an art, which is hard to identify as well, but it's an aesthetic activity characterized by elegance, simplicity, despite its complexity. And in particular, I think it's important to emphasize the simplicity, because the simplicity and the conciseness means that it's more understandable, at least if you're willing to accept some added abstraction. So a simple computer program, a small computer program, is a lot easier to debug and a lot easier to modify than something that's disorganized and goes on and on forever. And I think that it's important to emphasize that the simplicity and succinctness of the subject is really very effective. The roles of being a science, a language, and an art complement each other in a unique way. And this unique nature of mathematics leads to serious challenges in training, disseminating, and communicating the subject. But ultimately, mathematics is a fundamentally human activity. And let's enrich our society with communities of literate, knowledgeable, and creative mathematicians at all levels. So, thank you very much.
Thank you. I think we have time for questions. So, questions?
Yes.
So recently I've become very interested in like mathematical biology, and one of the big things that seems to be going on in that field is they keep on talking about how the models that they're working with are very diverse, yet they really want a language for like a mathematics for mathematical biology. So they, I guess the problem there is that they can't find what your term was the essential quality that's relating all these models. So what would you think would be the way to kind of start attacking that kind of a problem?
Probably by just listing what's known and trying to see if there may be some gaps in the list of the current list of examples. Not really. Just to try to see what looks like it would make the most sense, even if there's not all the phenomena have come into. Yes?
So, a lot of the presentations seems to be about. It's almost like the philosophy of mathematics, like in the sense that like this is what we should think of mathematics as, but. But if we are going to view it like that, then there are obviously different like other ways to view mathematics. I mean, there's Platonic mathematics, for example, where you think of mathematics as this very ideal thing that's like kind of out there, but like we can't really get at it. My question is like, do you think there's some like model of mathematics or like a particular philosophy of the way mathematics really should be viewed as that fits this sort of diverse, like a very diverse and multifaceted view that you presented?
I have no idea. I mean, the subject is still developing, and the mathematics doesn't disappear, and different subjects will become fashionable, and there'll be a breakthrough. So people are drawn to understanding the consequences of the breakthrough, and then that creates new mathematics. It creates a certain shift in the kind of mathematics, and there's been sort of a continual controversy between sort of more formal mathematics and more intuitive mathematics, and that certainly has been going on for a long time, and it continues a lot now, and I think a lot depends on what people get interested in. And so this is where the sort of community aspect is important, because it's not just a bunch of abstract ideas getting published and refined. It's a lot depends on what mathematicians are doing. And Susan mentioned that I worked and was influenced heavily by the late Bill Thurston, and I recently read an article that he wrote about the nature of mathematics called "On Progress and Proofs in Mathematics" in the Bulletin of the AMS in 1994, and I seriously recommend reading that article. It has a lot of interesting ideas and some rather provocative ideas about the nature of mathematics and how it grows, and how it's not just a collection of facts that are being recorded and documented, that it really is a community activity, and there's a lot more.
It's a human activity.
Yeah.
That's something that kind of, I mean, when I think about it, it makes sense, but I don't know, it makes sense when you say it, like, but that's not like how I would usually do mathematics.
But it's changed a lot in recent years with technology. And I think, having computers around has really affected how we do mathematics. And I resisted for a very long time, and I think it was actually a lot of the influence of Thurston who finally encouraged me to start writing programs and trying to look at some of the objects that were coming up in my research. And it was really quite surprising. I knew it was going to be a big time sink, and I resisted it because I didn't really want to spend a lot of time learning to program and debugging, and it was a big time sink, continues to be. But I think it does give a different perspective on the subject. And people will ask me, does it help you prove theorems? It's a very hard question to answer. You know, and sometimes I would find that it's like trying to explain something to a very weak but obedient student that you don't really expect the computer to generate any new ideas, but it'll do exactly what you tell it to, which is not always good because you may be telling it the wrong thing. But what I found was that just being able to write code that would do the mathematical calculations correctly helped me a lot because it forced me to be very precise. And then some of the objects that I wanted to study I thought were fascinating mathematical constructions. I would get a picture of them and I couldn't understand them. It was like spaghetti, you know, it was just too complicated. And I would keep going back and looking at simpler and simpler things that I thought I would understand. And we like to use the word trivial. And so, you know, things that I thought were trivial, I would draw a picture of, and it would be very interesting and much more striking than I thought. So it's understanding exactly how the technology helps is, it's very hard for me to pin down, but it's quite fascinating. But, you know, sometimes when I hear, I'm usually a little bit afraid to ask questions when I'm at a seminar or a colloquium, but usually when the speaker says something like, this is trivial, I feel like that's a good opportunity to ask what's going on. And sometimes, depending on the speaker, the answer to explaining why it's trivial will take up the rest of the hour. Yes?
Among the features that you mentioned that are necessary in developing a mathematician is the ability to learn and work with abstract ideas. And then you added, and to communicate them clearly. How well do you think graduate schools are doing with that second feature of having their students be able to communicate clearly abstract ideas?
Well, I think we're trying, and I think we're trying to address the problem.
What grade would you give them at the present time?
I have a hard time knowing what to say.
How about at the University of Maryland?
Right, well, that's what most of my experience is. I'd say we're, yeah, I don't know, A minus maybe, B plus. Maybe I'm an easy grader, but I don't know. I think, well, for various reasons, we have we have a large department, we have a large graduate program. It's a state university, and we're having always tight finances. So most of the graduate students are getting supported as teaching assistants, and they're getting a lot of experience in front of the classroom. And I think that's one thing. In recent years, there have been a lot of seminars and activities that are springing up where the graduate students are working with each other and giving lectures. And I think this is maybe the place to start. Is, you know, oral presentations and talks and seminars. But it's tough. It's like, you know, learning a language isn't easy. But I think the need for it has to be recognized, and that I think has happened. Yes?
I'm wondering what an experimental geometry lab is, and how is it used to help understand geometry, and how is it also used to teach it?
Well, what we've been doing, so we've largely been developing software, but it doesn't need to be. And the model that I've had, so this was also something that in the early 90s, there was a large project set up at the University of Minnesota called the Geometry Center. And it was a very high-level project to use, starting to use some of the supercomputers that were at the University of Minnesota, but eventually it evolved into other things. And unfortunately, it was shut down, and it was very expensive and elaborate. What I wanted was something that was a lot smaller scale and wasn't nearly as expensive to run and more directed towards some of my research questions. So we started with projects in non-Euclidean geometry and hyperbolic geometry and developing programs, and eventually we started just working in Mathematica, although that's just a convenient platform. And some of the style that I was trying to encourage with the students in the lab were to write code that was very dense and very short, but with lots of documentation. So it was maybe 10% code and 90% explanation, so that somebody that was interested can go back in and look at the computer program and modify it and understand what was going on. And so the idea was to have a collection of software that could be easily run, that would be very interactive, and then people could use the software to learn the subject at the same time as developing the subject. It's very interesting too, because you're kind of developing the mathematics as well as developing the software. So you can have experiences where something's going wrong and you don't know if it's the mathematical theory or the computer program. And when I was working in complex hyperbolic geometry and going up to Minnesota, I had shown that two different ways of describing a sphere were the same, but when I had the picture, one was twice as big as the other one. And I didn't think the theorem was wrong because I knew how to prove it, so I was led to looking at the code, but it could have been the other way around. And so it's in some sense a lot harder because you don't know whether the theory that you're basing the program on is faulty or not either. But typically the programs are pretty small but very dense and very critical. So a little mistake can mess things up very, very badly. So what we've been doing in the lab has been to basically study and learn the mathematics interactively by developing the software and interpreting it. And a lot of the students we're getting have not studied hyperbolic geometry, but have learned sort of the basic undergraduate courses, and the first step is to train them in hyperbolic geometry and group theory and some of the things that are needed, and the software is a fast way of getting them involved in it. Yes. Okay.
So I don't know how much truth there is to this statement, but I read an article recently that several undergraduate math programs, there's sort of been more of an emphasis on analysis and algebra, and less of an emphasis on the subject of geometry. I mean, if you look at like many graduate programs, like they require you to take. They're required to take a year of algebra and a year of analysis, but oftentimes they'll be okay if you either take like maybe just geometry, just topology, or maybe if you don't even take them at all. So, but when you look at like the subject of mathematics as a whole, geometry is like, I mean, that's an entire branch. I mean, that's a really big part of it. So my question is like, is that something like? I mean, do you feel like geometry is sort of in like a crisis of a sort? I mean, maybe not that like extreme, but do you feel like there's a need to push geometry more in undergraduate math education?
That's an interesting question. My tendency is maybe no, because I think maybe geometry is so prevalent, I think that it motivates the questions, but I think that as far as the technical tools for doing mathematics, and this is just my opinion, it would probably be more in an algebra and analysis. I think I'd be happy, going back to the University of Maryland graduate program, I think it would be improved, for example, if we just had qualifying exams in algebra and analysis. You know, and I think that in some sense subjects like geometry or dynamics maybe are points of view and ways of formulating questions, but the sort of mechanism and the language that what needs technical proficiency is algebra and analysis. That's my opinion, and it's subject to change.
One theme of your presentation that got me thinking and asking me questions was when you discussed how math is a science, a language, and art. And when you talked about how math is an art, you showed the image of the Parthenon and demonstrated the mathematical concepts that were used in the design. And I was sort of thinking about what aspects of math I felt made it an art, because I understood how mathematical concepts were being used to create art, but how math itself is actually an art. And I was curious if you had anything to add about that.
I find it quite fascinating, but I don't know if I have anything I can actually say.
Yeah.
But you know, I mean, there's a certain beauty that you have in this continued fraction. I mean, I think that's a beautiful. You know, that formula for the golden ratio as an infinite continued fraction, it has an elegance and a beauty once you say what that formula means. And so that's where mathematics itself is the art and the aesthetic element there. But you know, so it goes back both ways. The visual arts, and well, music also is very mathematical. There, you know, but then mathematics itself is an art, and
like
I think people are exploring.
In the concepts, not just in the objects. The concepts that
Right.
you create.
So maybe they're all part of one big subject. I don't really know.
Anything else? Well done. We should thank our speakers. And we should have cookies and refreshments, assuming there's still some outside the door. And we can continue the discussion.